Thank you very much. So first, thanks the organizers. Well, thank the other organizers for hosting me in this nice event. So this is actually a recent work by some of my colleagues from NYU and myself. So yeah, so it's pretty recent. So if there's some bugs and everything, just excuse me in advance. OK, so the starting point is, let's say, I would say like standard and to some extent a bit dull, because as we know, we are still in this kind of circles thinking about this supervised learning setup where our colleagues in DeepMind and like in other applied areas, they are already doing, as you know, much more crazy things like that go much beyond this setting. But already, what I will try to argue is that already in this setting, we have a lot of interesting and kind of intriguing properties, right? So that's the standard setup. We have some data coming from some distribution, some parametric model that we can think in high dimensions, and a convex way to evaluate the model. And we are also placing ourselves in the context of, like gradient-based learning. And already, as we know, just from this single setup, like single equation, there are already many, many questions that kind of entangle like topics that completely span like many different areas of different math and statistics. So during this workshop, actually, we have seen already these questions sort of touch each other in different talks and different regimes. So just here to cite a few, we know that some of the things that Andrea mentioned the first day were that if we care about approximation, we can tap into the kind of, let's say, classic theory from neural networks, like the second or the first wave of neural networks, already some years ago. We have already been seen today, in this morning, by Ohad Shamir talk, questions about the landscape of optimization, so trying to understand for what is the interplay between the architecture and how hard it's going to be for gradient descent algorithms to operate in these landscapes. And also, recently there has been a lot of papers that really insist in this regime in which basically having networks with many parameters somehow enables us to understand maybe things in an easier way than if we are in this kind of under-parameterized regime. So I'm assuming that Jason is going to tell us a lot of things about progress in over-parameterized networks. And we also saw yesterday, Nati and Sasha this morning, how this interplay between number of parameters and generalization works. So here, one way, at least for us to think about this problem, is somehow to come up with let's say like the simplest possible, how much we can simplify the game so that we can kind of isolate like some kind of essential properties that we care about the problem, right? So in this kind of very simplistic neural network architecture that has a single hidden layer, we already kind of obtain or isolate like three dimensions, three axes, right? So there are three orders of magnitude that we care about, is essentially how large is the statistical problem, like what is the dimension of the data, how many neurons we have, so basically how many parameters the network will have, and then how many data points we have, right? And so in this context, our function approximation is basically has this interesting form, which is basically a linear combination of some functions that are parameterized being some parameter, right? And think about these functions phi as being, for example, the result of some nonlinear activation function. So this setting is actually very similar to what Andrea described yesterday. Okay, so in this work, similarly as Andrea, we are interested in the regime where L is very large. Okay, so we first let L go to infinity, so number of data points goes to infinity, so kind of disappears from the picture. And then we are interested in understanding what is the regime when the N is very large. Okay, so in that sense, we are simplifying with respect to what Andrea described, because we are not interested in the interplay between N and L. And so what we also saw is that when you scale this model appropriately, we'll see it next, we can understand the dynamics of optimization, like what gradient descent follows in this regime, through some like partial differential equation that has some interesting properties. So in this work, what we are going to describe is a way to modify these dynamics that you get in that regime that use something that we call the birth-death process that we will describe exactly later what it means. And so these dynamics, they come with some that they are interesting in the sense that they allow us to maybe go prove some convergence properties of the corresponding model. And even though we have gone to this limit of n goes to infinity to define them, we can go back, right? We can re-implement these dynamics in finite n and carry out some of the benefits that we obtain, carry them down in the finite n. So that's the program for today. So just getting a little bit more specifically, so we are again going to simplify. So we assume no noise in the target. So think about this as some kind of like a, like a function, like a blended function that is in L2, and you know that from this universal approximation results that this function can be approximated when n goes to infinity. Okay, and so in our case, our neural network just has a single hidden layer, so it's parameterized by a family, like every neuron has carries its own parameters that encapsulate the input weight, the output weight, and the bias. And so when we use the square laws at the output, what we, again, also something that Andrea described yesterday, the loss with respect to the parameters of the model, it becomes a loss that, of course, has this kind of quadratic nature. So it has one term that basically averages over the parameters according to different neurons, and another term that looks into the interaction between pairs of neurons. Okay, so that's very natural to look at this problem as a system of interacting particles, right? So now we are going to associate each of the parameters theta with a particle, and then we have some objective function that depends on how these particles interact with each other, also under some external potential field, right? So actually, there's one case that we are also going to describe that in a sense is interesting. It's like a simplified version of this setup. That is the case where there's no interaction. So let's say that now I have a function that has this form, right? So basically, it looks like I have n different particles, and I'm interested in how well do they do on average, right? And so this setup is interesting because in a sense it corresponds, it maps very well with these problems that we call like evolution strategies or population-based dynamics, right? Where I have, instead of having just one set of parameters that basically moves around, tries to minimize a function, I have a bunch of them, right? And the goal of the game in that case is to try to organize the population such that they can explore better, right? And so there are some classic strategies in that regime, classical frameworks that fall into this framework. Okay, so so as I said, to try to understand a little bit more what's happening, we need to take the number of neurons to infinity, right? And so I just put here two natural scalings, but I mean, in a sense, there are two, let's say, canonical ways where one could think about doing them. The first one, in the case, is what I call like just to notation. So this, if you remember here, so I didn't tell you how I'm going to scale these networks, but now I'm going to say that, right? Because so far, I just described a system of finite neurons, so I don't really care about this alpha. But now I'm going to study the limits, right, when n goes to infinity. So I first might prefer to choose a scaling that basically has this kind of L2 signature, right? If I scale things on 1 over square root of n, the object that converges in basically in a space that converges in L2, right? And actually, one can show that in that case, these functions that are generated like this, when n goes to infinity, you can encapsulate them into a reproducing kernel Hilbert space where the kernel that generates the space is actually explicit. So I think it was already mentioned yesterday that there's this very recent paper appeared in NeurIPS last month where this kernel is studied, and there's some statements that can be done like that. But in a sense, this kind of equivalence has been also studied like some years ago by Francis Bach in a series of two very nice papers. So that's one way one can do it. But there's another way, as Andrea described yesterday, that where instead of scaling things in L2, you can scale them in L1. Right? In other words, in that case, the limit object, in that case, converges to a measure, right? That basically lives in L1. And so this is the thing that we will adopt from now on. And so, and if you are interested, and for more, I know that this topic about scaling and initialization is not completely settled. I mean, there are some interesting opinions, one on the other. So there's this very nice recent note by Leonic Shiza and Francis that kind of discusses these two. But for now, let me just adopt the L1 setting and see how far we can go. So in that case, if I look at the just again try to simplify things. So let's get rid of the learning rate. So we just go into continuous time. We have every neuron, every particle has an associated gradient, which is the gradient of the loss with respect to that set of parameters. And in a sense, it's actually very insightful to think about this gradient as actually a velocity. Basically, it's a velocity that is part of a velocity field. Right? And so now what I have is basically in the limit, I can think about my density as being influenced by a velocity field. And so if I think about the energy in terms of the measure, so here the only thing I'm saying is that I'm kind of identifying a vector of parameters theta with a set of Diracs that basically that are placed at the corresponding locations. So now one can interpret this, the idea of basically moving every parameter as the effect of letting this density be evolve according to what's called a Liouville PD. And this is as mentioned yesterday by Andrea, this was very intriguingly observed by many papers at the same time, which is kind of I think it's an indication that this is actually an interesting idea. It's very rare that it appears with 4 papers actually in the same time. Anyway, so that's the resulting dynamics with respect to the measure, and I'm just and actually I tried to use the same notation as Andreas' talk yesterday, but maybe I failed. I think there was the kernel was called U, and then I don't know if this was called V or F, but anyway, I tried to follow the notation just to make things simpler. And as again, one should interpret this PDE in the weak sense. So in the weak sense, what does it mean? It means that if I have a test function phi, I can, if I look at the moments with respect to the measure mu, the partial derivatives follow this PDE. Okay. Okay. So and in fact, I mean this PDE can be again even more compactly understood by basically seeing the same evolution of the density. Is actually you can actually see it as what's called a gradient flow with respect to a metric in the space of measures that is the Wasserstein metric, right? So the way to think about it is that the evolution of the density is the one I would follow if I try to follow like steepest descent of this energy here that I described, where I measured the metric with respect to the Wasserstein space. Okay, and so this energy in a sense is very, very simple. Because in the case of a quadratic loss, it becomes a quadratic form, and in the case of non-interacting potential, it becomes a linear function, right? So if there's no interactions, this is just a linear form with respect to the measure. And so this is a functional that applies for measures that are either like defined, like that are regular, that have a density all the space, but also for discrete measures, right? So basically, this formalism also applies to the case where n is finite. So one natural question that these papers addressed is when is this dynamic going to converge? Or under which conditions this PDE is going to converge? So again, non-exhaustive and trying to simplify what these papers partially, like they basically came up with different angles to study this question. So the first one by May, Montanari, and Nguyen, as Andrea described yesterday, what they managed to prove convergence by simplifying the dynamics by adding like a diffusion term, like a Gaussian noise, that basically gives enough smoothness to the solution to guarantee convergence. There's another angle that was exploited by Leonic, by Shizak and Bach, where in that case the idea was to exploit like specific homogeneity properties of the functions, of the activation function, to actually guarantee a global convergence. And then there's another recent paper by Javanmar, Mondelli, and Andrea, where they use a completely different technique to get convergence using what's called like a displacement convexity. But another, like in between these two, there was another paper by Jason, Wei, Liu, and Teng Yu Ma, where they, also using the same framework, they proposed a different way to modify the dynamics by re-injecting a fraction of particles at each step. And that was, and thanks to that, they could get like some kind of like a approximate convergence, not to the global minimum, but to some kind of like perturbed solution. And it's actually thanks to that, thanks to this recent paper, that basically we got the inspiration to do something along the lines. But instead of just reinjecting particles from a base density, we do something slightly different. So this is the thing that we propose, is that instead of just doing basically following the gradient, doing a transport equation, we are going to modify the dynamics by adding something that looks a bit weird at first. What we're going to do is that basically we are going to rescale the dynamics. We are going to modify the dynamics by something that is non-local. Right? It's not a local transportation term. And so here we have the current potential energy that is basically like a kind of energy with respect to the parameters and the density. And that we are doing is basically we are subtracting this term and adding its average, right, with respect to the density. And so it's very easy to verify that when I add this term, if I integrate these two terms with respect to the measure, right, by definition, if I integrate this with respect to the measure, right, this term, and so if I integrate here and here, what I get is by construction, by definition, this term does not change the mass, right? So basically, it's a kind of a legitimate way to transport a measure, right? The mass is preserved. But the mass is preserved, but in a sense, the mass can move in regions that are not local. So why do we want to do that? Why is this a good idea? So yeah, before going that, let me mention something that, of course, in the previous model, if you go back here, right? If this density here, mu t at a given point, I'm exploring a bunch of finite number of neurons, right? So the only thing this thing is doing is kind of reweighting. If you look at these terms here, if these terms, if mu t is 0, I mean, they only change things in the support of mu, right? I mean, if mu is 0, this thing doesn't change. So one could say that, we are basically doing something non-local that is meant to explore faster, but it cannot explore beyond the support. So in that case, what we can do, I mean, what we do is doing something that's slightly more complicated. It looks a bit more, it looks much more complicated at first, but believe me, it's not much complicated. That uses a prior measure. So think about, this is a bit more related to what May and Jason did, right? So let's assume that we have a base measure, and we are going to do something that is kind of easy to understand, right? So if we look at what the contribution of the first term, right? What happens is that basically this term, basically what it does is separates the space of particles in two regions. Basically the region where the current potential is positive, which means it's bad, like the bad region, and the good region is the region where the potential is negative, right? Remember that we want to do is that we want to try to minimize the potential. And so with the first term is that what we do is that basically we try to look at when in the regions where in particles that are in this region are going to be killed with a rate that is proportional to v. And then we are going to re-inject the particles that we have killed in the region where we believe the potential might be better. And we use the base measure to re-inject particles in that region. And the second term does something that is basically the reciprocal operation, right? What we do is that we have another way to explore in the space where the potential is good. So we basically prop particles here according to the base measure. And if we find particles that basically minimize the potential, then in order to preserve the population, we need to kill. So which ones are we going to kill? We are going to kill the ones that are currently in the bad areas of the potential, which are the green areas.
Why is 0 have a particular meaning here?
Well, I just centered V. So basically what I do is that...
What the alpha does?
So the alpha, yeah, so these are basically two parameters that basically reshift mass from good regions to bad regions. So the fact that I have the threshold at 0 especially is just that this is the mean of the potential at this point. Yeah.
So can you describe a little more what the minus alpha v mu and plus alpha v bar does?
Yeah, so this is basically...
If I didn't have this threshold in chart, for example.
So if you just think about like one of the two, I mean, both are doing the same thing, right? So the idea is that you basically have some current mass. So let's look at this. Let's look at this thing here, right? So this is basically going to create new mass in the regions where V is currently negative, so like good regions, according to some base measure mu V. And then a mass that is created has to be destroyed, right? And the mass that is destroyed is proportional to some rate that depends on the potential in the bad regions of the film. Okay? So just observe by using this definition of, yes?
How do you create obstacles with it? I mean, algorithms.
Yes, I will describe the algorithm later. So it's a very good point because in that case what we have is we estimate the potential using a batch, and with this we assign a probability to every existing particle, either to be created or to be cloned. Okay, what we're going to say is like a procedure to do cloning. Okay, and then the base measure typically we will describe it later in the experiments, but we use a relatively naive way to do that. Okay, so if you think about the sorry, at what time did that start? Sorry, at what time did that start? Sorry. Okay, perfect. Okay, so if you test this evolution with respect to the function v, right, you get the evolution of the energy, right? And so it's very easy to see that if you test the PDE, if you test the dynamics with v, what you get is that basically the rate in which the energy decreases, you get something that has the right sign. So this is the standard transport term. And what you observe very, very kind of remarkably simply is that adding this new term, these Bertha terms, if alpha is positive, what you get is basically that the rate in which the energy decreases is strictly improved, right? You get, by adding these terms, you are only making the energy get decreased faster. Okay? And this is just because the thing that you are, the perturbation that you do in the dynamics has an effect that this basically term is strictly non-negative. And so, and it's easy to check that with the other version with the base measure, you get the same trick, right? So this is basically an elementary thing that says that for every time t, the rate of decrease of energy is improved, right? It's never bad at the mean field level to do that. But the question is, can you use this? So this is just non-collidative, right? This just says that one derivative is larger than the other. Can you get this to get convergence rates? So we start by the simpler case where there's no interaction, right? Where the potential is actually non-interacting, right? So in that case, you have a function v that is just imagine this v as an arbitrary non-convex function, right? That you want to minimize. And we make an assumption that it's coercive, so basically it goes to infinity when that parameter is very large, and it's sufficiently the gradient of v is Lipschitz, right? Lipschitz beta. So in that case, if you look at the corresponding birth dynamics, what we show is basically that the dynamics converge, and converge with a rate that is basically 1 over t divided by 1 over t at 1 over d, right? Basically, the time it takes, if I want to make the error epsilon, right, I need to wait a time that is basically of the order of epsilon to the minus d plus 2 over 2. T epsilon, yeah, sorry, T epsilon less than that. Yes. Yeah, sorry, this is T epsilon, okay? So what we have is basically global convergence if the initialization is smooth. So this is similar to what some of the Andreas paper. And the thing that is behind this result is essentially a Riccati equation. I think it was mentioned in the previous talk that is basically a quadratic equation. And the quadratic term really comes here, right? If you look at the energy, as you know, in the case of non-interacting, this is an integral of the potential times the density, right? So you have basically here some kind of quadratic term, and this is where you get this kind of thing that looks like 1 over t. It comes from here. And probably this dependency on the dimension is not sharp, so this is proved by elementary techniques by people like me who are not at all experts in PD, but already you get this kind of nice thing. And so it's to know that this is very different. So if this thing was not here, right, you would not get that kind of result, right? The only thing that you can get is basically convergence to a stationary point, right? The place where the gradient is 0. So as I said, the previous rate is pessimistic in the sense that we can make an argument that instead of deriving a global rate, we can derive like an asymptotic, like a local rate, like a fast rate, which means that when we are by assuming that the function is Morse, basically that at the critical points there are no eigenvalues that are 0, what we have is that for t sufficiently large, right, the behavior of the energy looks like basically behaves as something that looks like an exponential rate, right? So basically what you have is you have something here where time is in the exponent, right? And so here, again, not surprisingly, is that when t is large enough, when we are sufficiently close to the solution and the potential is sufficiently smooth, right, what you get is basically you inherit the linear convergence that you get from just transportation, right? If you try to do transportation on a function that locally looks like it's something convex, you get linear convergence, right? That this is for t sufficiently large. So again, what is interesting is that, in a sense, what you see here at play is that the two kind of parts of the dynamics are helping each other, right? So like the non-local, like the Berther term is actually helping you to get robustness to get global convergence, right? It helps you escape local minimum. But once you are in a location that you have escaped, then the transport term take over, right? And they get you like the fast convergence. So how about the interacting case, the general case? So here we are, again, settling on a case. We need to make an assumption on the kernel that we call like weakly interacting, right? So when I say weakly interacting, here what I mean is that if I look at two particles that are sufficiently far, when the particles are very far, they should not interact very much, right? And unfortunately, this rules out. If you look at the kernel that you would get from a ReLU activation function, you can see that this is not necessarily the case, right? You can have in the kernel derived from the ReLU does not fit into this framework. But in that case, what we get is, again, under some mild assumptions. So if the solution, like if the global minimizer can be realized, can be represented with a measure that has a density, that has an infinite Lebesgue measure, then in that case, we get global convergence. But here we have no rate, right? So here we have global convergence. In a sense, this kind of assumption, what it tells us is that we can basically avoid the stationary points that you have in the original transport equation. Okay, so this is a kind of a result that works by making some assumptions on the kernel. And so also we believe that we can turn it into a local asymptotic rate of 1/t by now something that we are currently working on by using basically the spectral decomposition of the kernel. One can get like asymptotic rates by working on looking at the eigenvalues of the kernel. But this is still work in progress. Okay. So far what I described is something that works in the limit where I have infinite particles, right? I mean, it's just a completely PD, right? So one of the questions of Andrea was, how do you design this in practice, right? So that's very important. And how do you ensure that the dynamics that you get for a finite n somehow inherit the nice properties that we described here? So in particular, you want to understand if you think about a version where you have like n particles instead of basically the density, you can think about the density that you have with n particles as a kind of like an empirical version of the underlying density that would have the underlying measure that would have a density. So how are the fluctuations that you get going to evolve with time, right? Are you going to get fluctuations that kind of amplify with time? Are they going to shrink with time, etc.? Remember that here all the dynamics are completely deterministic, right? I mean, nothing in the PDE is stochastic. So for that, we use again like a standard technique in PDEs, but maybe non-standard for some of us, including myself. There is this notion of like the infinitesimal generator of a PDE, right? So the infinitesimal generator is basically is something that you can use to measure how certain test functions on the measure evolve as you let the measure evolve with the PDE, right? So in the case where I just illustrate what happens here, in the case where I have non-interacting and no transport, right? So in that case, the dynamics are very simple, and you can write down the infinitesimal generator of this PDE. And so for finite number of particles, one can basically compute an infinitesimal generator that is kind of like the empirical infinitesimal generator, right? That you can basically work yourself what happens with the measure as you start like taking some units of mass in some discrete measure and putting them in somewhere else, right? And so in that case, what one can show is that the infinitesimal generators with finite particles in some sense, they converge to this infinitesimal generator. And so once you have this notion of convergence, you can actually compute a large deviation principle at the level of these infinitesimal generators. And if you test this generator on their test functions that look like this, we get, again and again, at this point, we do something that is not claimed to be a theorem. It's more like a non-rigorous analysis. You can use this technique, this methodology, to compute a central limit theorem of basically the fluctuations of the measure around its mean, right, around the continuous time. And so what we get is basically, what you know is that the fluctuations, once you rescale them by square root of n, they become Gaussian. And the covariance of the Gaussian field itself satisfies a PDE, right, and has this satisfies this PDE that, in a sense, that resembles the original PDE, but of course it's on the product measure. So the take-home message of this part is that the fluctuations are of the order 1 or square root of n. And if I just allow myself on a finite time interval, these fluctuations stay bounded, right? They are of the order 1 of square root of n. So at this point, one could say that, well, everything we're doing is kind of legit, right? If you have a system that has good behavior at infinite n, if n is sufficiently large, you are basically, this thing tells you that the finite system is going to basically evolve following the nice system with fluctuations of the order of 1 of square root of n. Okay, so how about the algorithm? So how are we implementing this in practice? So in fact, I mean, in practice, what we do is something. Actually, the implementation is actually very simple. Is that we compute this potential, which is by definition the loss, in the loss, the contribution of each particle in the total loss. And we estimate, because this loss is an expectation over the data, as I described at the beginning, of course we have to settle with an empirical version of that because we just estimate this quantity over a batch, right, of a certain batch. And so if the current contribution of the particle is large, it's like larger than the average, we kill a particle with a probability that depends on the rate, right, on the current rate. And if the particle if the contribution of if the particle looks good relative to the rest, we are going to clone it. We are going to basically duplicate it with a probability that is basically following the inverse probability. And then after we have done that, we make sure that the number of particles does not change, right? So we do population control by either killing or cloning particles if the first step of the algorithm has changed the number of particles. And so as I said, there's one version of the algorithm in which we use a base measure, like a prior measure. And in the case, one could ask, how can you create a new particle in a way that it's not going to mess with the energy, right? That you want to put a new particle, but you don't want this new particle to suddenly make your energy go bound, right? Remember that at infinitesimal time, what I described is that I can putting this birth term always makes the gradient of the energy strictly larger than it was before, right? So you would like, at finite time, you would like to have the same property. So in that case, we use one specific property of neural networks that is very easy to put a particle in a way that it doesn't do anything. You just put the position where you want, and you put the output weight to 0. If you put your output weight to 0, this particle does not do anything, right? And then the gradient descent will start moving it around. OK, so I'm going to just show you a couple of numerical experiments. The first one is we have like a kind of you can think a mixture of Gaussians as a kind of a planted Gaussian model, right? They have a bunch of Gaussians at different centers with different variances and with different like linear combinations. And then what I try to do is I try to recover this mixture of Gaussians with a neural network that has a Gaussian activation function, right? So in that case, the function that I have looks like that, right? So if I have more, the game is pretty simple. I have basically I have a landscape. I have a function with a bunch of Gaussians, and I need to approximate this function with Gaussians that I will move around. Okay, and so we are going to use an overparameterized model. So we are going to try to put more Gaussians than we have. And so what you get, if you do gradient descent, you get like the loss goes down. But if we implement our scheme with like a birth-death terms, so either with or without the base measure, we get a convergence that is much faster. And in any case, I mean, eventually both things end up approximating the right function. And we also, I mean, one can also try to be like evil, right? To basically initialize these dynamics in the wrong positions, right? So in that case, we do the same game, but using like a bad initialization for all the algorithms. And unsurprisingly, the algorithm that uses a prior measure is more robust to initialization, right? Because we can always create particles in positions that they were not seen at the beginning. And then we also have experiments like on the flavor of Shiza and Bach, where we have like a teacher-student network. So that's the setup that we have also seen already in these talks, is where I have a planted, like I have a function f that is a linear combination of, let's say, 10 planted neurons, and we try to recover them with 50 neurons. And this is using ReLU activations. And here what we get is essentially the same story, where when we apply our modifications of the transport, we get something that converges on average, like this is in log scale, so like basically a couple of orders of magnitude faster, like lower than the original dynamics. Okay. Okay, so this is this is nice. And so, I mean, of course, these experiments are small scale, and there are many questions that are still open. But here's, for example, one particular open question that I would also like to relate, given that yesterday Andrea described this topic in quite detail. So here's one way where one particular question that one can think to basically connect the two regimes, like the interacting and the non-interacting. So as I described, there are two settings, right? This is the one where arises when you train a neural network, right? Where you have a functional that is quadratic, right, with respect to the measure. And then there's another one that makes the analysis much simpler. That is the one where the particles don't interact, right? But if you use like a quadratic loss, you see that the interaction is actually pretty gentle, right? It's quadratic. So one question that we have is, why don't we think about this problem, instead of looking at the problem where the evolution is in the measure with respect to the parameters, we can think about this problem where now the measure lives in the product space, right? Where now I have a mu tilde that is defined in the product space. So in that case, I can define like an equivalent energy that in that case is basically that when mu tilde is actually the separable, is basically the product of mu, you get the original quadratic interaction problem. But now this seen as a measure with respect to mu tilde is non-interacting, right? Basically, in a sense, I make the space larger, and now I basically move from an interacting to a non-interacting regime. But of course, this is not as simple, because now, even though I can solve this problem using the techniques of non-interacting potentials, the solution that I care about is not any product, is not only measuring the product space. This measure has to be rank 1, right? Yeah, I mean, at the end of the day, the dynamics, they involve like particles, and I mean, the energy involves like a density that is basically a product density. So one thing that we are trying to understand is there a way where one can basically relax this notion that I need to basically solve a problem in the lifted space, but I would like my solution to converge to a measure that is low rank, right? That basically has low rank. So by the way, if there's any experts in how to leverage like low rank ideas for space of measures, I'd be interested to know your thoughts about whether this thing makes any sense or not. So just to conclude, so we presented this kind of simple, like gentle modification of these dynamics that in the mean field limit, they help the consistency, and they can help us get some like a convergence rate. And so we can also, I mean, these dynamics are not just, I mean, are defined in the mean field limit, but they can be implemented and studied in the finite particle case. And some preliminary experiments, they seem to suggest that the theoretical advantages that we see, they seem to be at least partially carried out in practice. So of course, we have no idea on how to do that if you replace the single hidden layer neural network by a general neural network. We don't know how to kill and create new particles. Can we have like maybe a principled way to choose the base measure? So this we don't know. And so with that, I will thank you very much. And if you have some questions, happy to answer. No, it's not a gradient flow anymore in that case. It's not local, so the dynamics are non-local anymore. Yes?
What happens if all of the neurons are in a place where the first variation in is possible? It's like they can't see the next.
So what we do, by definition, we center the potential, right? Basically, we always kind of organize the neurons in two categories: the ones that are larger than the average and the ones that are lower than the average. Yes. So the analysis of what happens when you have like empirical estimates of all these quantities, one has to be careful to analyze the fluctuations of that, yeah.
So do you have an idea of when this is proven that is convenient?
Convenient or non-convenient?
When it helps?
Oh, yeah, so we saw, I mean, clearly it helps because it, as similar as your both techniques, it creates like stationary points unstable, right? And so this already helps you escape these positions. And the other way but the other kind of interesting feature somehow is that it has like this kind of self-tuning mechanism, right? If your potential is small, by definition, these things are not going to change are not going to deviate you from the place where you want to converge. But to be honest, we are just recently starting to understand these things, so there are many things that we don't know, and in particular, I mean, at the end of the day, there's no magic, right? I mean, in a high-dimensional regime where you have to, if your particles are in the bad position and you have a prior measure, I mean, it's not by magic that you are going to find good location just by sampling. So I tend to see it more as a mechanism to basically escape bad configurations. Yes. Yes. So this is this idea that, I mean, if I have actually, so what time do I have? 5 minutes. Okay. So if you have a function that comes from a neural network, you have some output weight times some activation function with some weight, right? Let's say that there's no bias. So I can always create a particle where this thing is 0.
Yeah, but like once you put it, don't you want it to be actually some number so it doesn't always be 0?
No, because then the gradient, I mean, if I take the gradient with respect to A and the gradient with respect to B, it will start moving, right? I mean, in particular, it can choose the sign of this thing.
Thanks again.